Okay, let's play some damn spades.
In the mid-1800s, Michael Faraday gave a series of Christmas lectures for kids at the Royal Institution in London, and one of his favorite subjects to talk about was fire.
Look how damn ugly I look.
Faraday was particularly interested in candles because inside their delicate flames, they hold some amazing lessons on how fire really works. Like, you might have seen fire described like this in chemistry class, but a chemical formula doesn't explain what fire is any more than a recipe explains what chocolate chip cookies taste like. Like, you might have seen fire described like this in chemistry class, but a chemical formula doesn't explain what fire is any more than a recipe explains what chocolate chip cookies taste like. The first thing we notice about a candle flame is all those colors. Hot things glow because of black body radiation, which we talked about in our video about the color of the universe. And down at the bottom of the flame, it's hotter, so it glows blue. And in the middle, it's a little cooler, so it glows yellowish, orangish. Inside of that flame, there could be hundreds of chemical reactions taking place. The oxygen in the air and the carbon and hydrogen in the candle, they don't do anything on their own. It takes a little outside heat to get things started. Solid fuel is vaporized by the heat and ripped into smaller chunks. This is called pyrolysis, and you can't have a flame without it. You can sometimes see a dark cone around the wick where there's no fire. That's where vaporized wax is coming off the candle, but it hasn't started to burn yet. The hydrocarbons and oxygen in the air slam into each other, and their atoms begin to rearrange. Sometimes electrons in those atoms get into an excited state. When they come back down again, they give off light. That's why the bottom of the flame glows blue. Not all the carbon in the candle gets converted to CO2, so leftover carbon atoms come together and form tiny particles of soot, which heat up and glow orange and yellow like the hot coals under a grill. This glowing soot is where most of a candle's light comes from. Eventually, at the tip of the flame, all the soot is burned away, and we're left with only carbon dioxide and water floating off into the air. You can investigate all the different parts of a flame for yourself with just a cold piece of metal. Up here, we find water vapor. In the yellow part of the flame, soot. And down just next to the wick, we can even recover unburned wax. Flames look really cool, too. They're almost hypnotic. Wait, what was I talking about? Oh, right, shape. Gravity pulls cool, denser air down and makes hot air rise. And this buoyancy is what gives flames their familiar shape. But if you light a flame in 0 G, say on the space station, it'll look very different. All the chemical and quantum reactions that make a flame glow very different. In 0 G, say on the space station, it'll look very different. All the chemical and quantum reactions that make a flame glow can only happen where it meets the air. So even though they look like solid cones, candle flames are actually hollow. As long as there's fuel and oxygen, the flame will burn and burn. Why? See, it's not the molecular ripping apart that makes a flame hot. The formation of new molecules and new bonds is what creates heat, and that heat drives the chain reaction forward, vaporizing more fuel, slamming more molecules into one another, and making the fire burn on. Our species has been gathering around fire for thousands of years, telling stories, asking questions over a flickering flame.
Come on, slut.
And that's part of what helped make us human in the first place. Stay curious.
I was fixing to cuss you the fuck out. 1, 2, 3, 4. 1, 2, 3, 4, 5. Come on, slut. Come on, slut. Send out a card, slut. She spit. Oh, she's cute. Boop! I touched her head. I touched her head. That's what you call jack fucking. I jacked his fuck. I jacked his fuck. That whore, that whore, that whore, that whore. Now that means you not have spades. Come on! Send this fucking card. Slut. Yep. I knew it. Now don't you have a spade, you bad girl. Play to my damn. Play to my damn. Play to my damn. What? Dude, that girl was having no spades. Time to go fishing! Who's got that ace? Yep. That's who's got the ace. What the fuck? That whore, that whore, that whore, that whore. Man, you're fucking hole! Look how ugly I look. I want to kill myself sometimes. I want to kill myself. I want to fucking kill myself sometimes. If I can't be a fox, I want to fucking kill myself. I hate hand jobs like the one I got right there. This hand right here is a hand job from a tranny. This shit right here is a hand job. I'm glad it leads, but that whore, that whore, that whore, that whore. No. Look how ugly I look. Fucking middle age, but makes me want to fucking kill myself. Man, I'm sick and tired of looking like this. I want to fucking kill myself sometimes. That whore, that whore, that whore, that whore. That whore, that whore, that whore, that whore. Man, these people, man, these two opponents are not the sharpest dogs in the light socket. I want to kill myself sometimes. Well, no wonder. Come on, sit us down. What the fuck is that pee bitching about? I got juice. I got juice. damn clock stop working. It is fucking pissing me off. Get your slutty little ass. Time to go fishing! No. Man, the more I think about it, looking like I am, I'm just, especially if I don't like Jesus, I don't know. The more I think about it, the more I think about killing myself. I have to look like this, I can't get the hair transplants. Sometimes I just want to fucking, if I have to look like this, I want to fucking kill myself. I want to fucking kill myself. I want to fucking kill myself rather than look like this. I want to kill. I want to fucking kill myself sometimes. Nigga, I want to kill myself if I have to look middle age. Look at my hair. It's a fucking... I want to fucking kill myself. Slut. Fucking slut. Slut and fuck. That jack, that jack, that jack, that jack, that whore, that whore, that whore, that whore.
Do you ever question your life?
Rosy spit.
Do you ever wonder why?
Man, I think you're fucked.
Do you ever see in your dreams all the castles in the sky?
Man, we fucked up the butt.
Do we build castles in the sky? Tell me why. All the castles way up high, please tell me why. Do we build castles in the sky?
Yeah, I know. I jacked you up. That's why. Man, why am I getting all these shitty hands? All these hand jobs from trannies. All these hand jobs from trannies. They split. with their spits, with their splits, the split, split, split. All the castles in the sky. Man, I'm gonna go check if this thing keeps going slow like this. This fucking pisses me off. Slap! 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 Stop! Stop! That whore, that whore, that whore, that whore. Stop! Stop!
I can't believe I still receive so much affection from your side. If you could give me one more chance, I'd love to turn the tide. I can't believe I still receive so much affection from your side. If you could give me one more chance, I'd love to turn the tide.
Shit. I did a 15-book bid, and our team took it. That whore, that whore, that whore, that whore. Damn. That ace, that ace, that ace, that ace. That's gonna fucking piss me off when he gets straight. Pour the shit out of me. That damn ace. Well, he's got his. Now I need to get mine. That whore, that whore, that whore, that whore. 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 Man, we fucked there. Oh! Well, I'm not playing with bots. Fuck that shit. I remember her Pucky Q. Jesus Christ, can't hold it. Jesus Christ, can't hold it back. Jesus Christ. Jesus Christ, can't please hold me back. Can't please, Jesus Christ, can't please hold me back. Come on. Come on. Come on. Yawn!
You came to save the girl like an old-fashioned hero. You could have been anyone, but it happened to be me. The promises you made, I wanted to believe, and now I know it was.
That was stupid of you to trump my clubs. Shit! That fucking pisses me off. Good. I got my 3. You better get your 4. That whore, that whore, that whore, that whore. Oh, let me try something. See if I can give emojis on this bitch. You see that? I just call her slut. Whoops! No. That whore, that whore, that whore, that whore.
Joyless laughs, priceless photographs, our greatest prize in dancing, sparkling eyes, illuminating haze, ever long unable to breathe. In you I see perfection for me. You smooth me without any Please always love. Please always love. Please always love. You're my
Let's see if I can pull this fucking shit off. That's some jackass playing around. All I need is doing good. If I saw that whore, I don't know, we were fucked. That whore. With Uzi Emily. With Uzi Emily. One of these fucking spades. That whore. Don't fucking piss me off. Her form is lower than mine. Fuck. Please never let me kid. Please change this place. Please. Please. The child will be back. Can I? Please, please let me be back. Come on. Oh, an adorable female. Anytime there's a female in the video, I have to do this. I have to save her. Skip, 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 skip. Spit, 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 spit. Similar extra treat. Come on, Aqua Jackass. Man, these people are boring. Fuck this shit. I'm not playing with them. Why watch the commercials when you can watch these cute females? Man, this fucking pissing me off. Find me a table with some expert players. Man, this fucking pisses me off. Find me a table with some expert players. Ah, I like Mary Beth. There's Pick Beth. Come on. That whore, that whore, that whore, that whore. Damn, it's time for the atomic bomb. Come on, slut, bid. That whore, that whore, that whore, that whore. Please have something to beat that whore of diamonds. Come on, slut. I'm not worried about those damn clubs. Man, that's fucking pissing me off. Son of a bitch. Is that whore gonna hang me? Man, I hate seeing these fucking Spades flies. Man, that fucking whore hung me. That fucking pisses me off. That fucking whore hung me. That whore, that whore, that whore, that whore. The damn thing of heart took that shit. Son of a bitch. That fucking pissed me off. Let's see this from... I cuss. This is not supposed to be able to cuss in this game. But I do it anyways. Okay, it's time to get suicidal. See how I look. That fucking king. That whore, that whore, that whore, that whore. Look at that damn king. Oh, that was that whore, that whore, that whore, that whore. That was dumb. Those two fucking spaces bother me. That fucking pisses me off. That fucking pisses me off a lot.
Sometimes
That whore, that whore, that whore, that whore.
Words don't say what you need. Explanations are not what they seem.
That's not a female singing.
Your heart's not in it. I can feel you no more. Don't take your answers. Walk out the door.
That king.
Can I hold you just a little bit longer? Can I breathe you in before I
Hear him sucking up them bags.
will touch away from the
Damn.
touch away from the dark?
We both got a fucking bag. Shit.
Till the night closes in.
Oh, she's cute. Man, this is a shitty hand. Man, I hate hand jobs like this. This is a shitty hand.
Can I hold you just a little bit longer? Can I breathe you in before you say goodbye?
Man, somebody took my hand and wiped their ass with it. You can't nail it, you can't bit it. Somebody gave me a hand job for the tranny. This shit right here is a hand job. Fucking hand job. Shit.
The night closes. The night closes.
Came the shit out of that. That whore, that whore, that whore, that whore. That whore, that whore, that whore, that whore.
Thank you very much, everybody. It's a wonderful pleasure to be here at the Royal Institution. This is my favorite lecture hall to talk about science in. Of course, other people have talked about science here before me. There's this wonderful legacy that we have, this wonderful history of not just lectures, but demonstrations here at the Royal Institution.
Come on,
from Michael
somebody click the
Faraday
button.
to Humphrey Davy. And I'm a theoretical physicist. I feel like I'm at a disadvantage. I don't really do demonstrations, but I thought it's the Royal Institution. I should at least try to do some sort of demonstration. So we're going to try. There's no guarantee of success. That's the beauty of science, right? You never really know. So here's what's going to happen. I am going to push a button, and my phone
Now I
is
got
going to
another
send a
damn
signal
hand job.
across the internet to a laboratory in Geneva, Switzerland, in which a little gizmo will send a photon, a particle of light, toward a partially silvered mirror. And according to the rules of quantum mechanics, the photon will in part pass through the mirror and in part be reflected off. There will be detectors that will find out whether the photon went one way or the other. And once that happens, quantum mechanics says, there will literally be two different universes created. One in which the photon went one way and one in which the photon went the other way. A signal will be sent back to my phone in which that will be translated into instructions to either hop left or hop right, which I will then do. Let's see if Michael Faraday could do that. Here we go. Okay, and again, this is not a simulation. This is really actually happening. There really is a little beam splitter there in Geneva, and it's telling me that I should hop left.
What a fucking door.
I did it. Thank you. You've been a great audience. Thanks. No, there's more to come, but the point is, according to the theory that I'm going to try to explain to you, and maybe even persuade you of its reasonableness, there literally is another version of the universe that is just come into existence, where a version of me is standing there and going like this. And I actually believe this is true. And maybe you won't actually believe it's true, but at least you'll understand why someone like me would believe it's true when all is said and done. Okay, now this is the hardest part of the demonstration, which is working the PowerPoint. Is it working? Yes, there we go. Okay. Of course, the topic here is quantum mechanics. If you're not here to hear a lecture on quantum mechanics, something has gone terribly, terribly wrong. But the reason why I would like to talk about quantum mechanics, the honest reason, is because I've written a book about quantum mechanics that you could buy right now on your iPhone without leaving your seat. But if you know even a little bit about quantum mechanics, your question should be, why in the world do we need another book about quantum mechanics? And I think that there is a reason, and the reason is
Suck them bags.
implied by this famous quote by my Caltech
King
predecessor,
Shiverin.
Richard Feynman.
Fuck.
I think I can safely say that nobody
That
understands
whore, that
quantum
whore, that
mechanics.
whore. That
Now, I
fucking-
usually don't
that
like to
fucking
appeal to
pisses me
authority when I'm giving these lectures, but when the thing I'm trying to demonstrate is that physicists don't understand quantum mechanics,
Man, I
I'm allowed
couldn't
to
got
appeal
those
to someone
chicks
who
if I
anyone
had
should have
been five.
understood quantum mechanics. What in the world does it mean for someone like Feynman to say no one understands quantum mechanics? He used quantum mechanics every day. In fact, we can use quantum mechanics to extraordinary precision. We can make predictions. We can do the experiment. We can see the outcome. The rules of quantum mechanics are obeyed. The problem is we understand quantum mechanics and use it in exactly the same way that I use my iPhone. I can send signals, I can use apps, I can send texts, even phone people on my
Man, I shouldn't
phone.
have
But if you
done
say,
this.
what's going on inside? How do I build one of these? What are the details? I have no idea.
Man, I shouldn't have kneeled like
That is the
that.
relationship that professional physicists have with
fucking
quantum
pisses me
mechanics.
off.
They can use it, but if you ask them what's really going on under the hood, they say, well, we have no idea. And that's perfectly fine when it's me and my phone. It's really embarrassing when it's me and when it's physicists and quantum mechanics. And the really bad thing is not just that physicists don't understand quantum mechanics. Not understanding is perfectly fine. Right? Not understanding drives science. We don't understand something, so we then try to understand it.
That whore,
The
that
problem
whore,
is that in
that
the case
whore,
of
that
quantum
whore.
mechanics, we don't even try anymore. There was this time in the 1920s and 30s when the greatest physics minds really thought deeply about what it means when quantum mechanical events happen, but then that disappeared. That project of trying to really deeply understand what's going on. It was thought to not be serious work. It was thought to be what one did at the end of one's career, or at the end of the day. There was a little brandy, you put on your smoking jacket, and you think about quantum mechanics. It was not really what real physics is made of anymore. So if you ask many physicists today, like, what's really going on with quantum mechanics, they'll say, no, we don't care about that.
That
We don't
whore,
want
that
to know.
whore, that whore, that
So
whore.
the metaphor, the parable that I'd like to borrow from is Aesop's fable of the fox and the grapes. You know this one? The fox sees that it's a nice juicy bunch of grapes up there. Goes, oh yes, I want these grapes. Fox jumps up and down to get the grapes, but the grapes are just out of reach, just a little bit too high. So the fox says, you know what? I never wanted those grapes anyway. They're probably sour. You're not supposed to explain your parables, but just to make things clear, the fox represents physicists.
Woo!
The grapes represent understanding quantum mechanics, okay? Physicists tried, they failed, and now they've convinced themselves they never wanted to try. And I think that that's wrong, and that's embarrassing, and we should do better. So I have an idea. It's not my idea. I have a favorite version of quantum mechanics I would like to pitch to you. But much more important than my favorite version is the idea that we should be able to understand it. It's not mystery. It's not magic. It's just science. So let me remind you where quantum mechanics came from, why we invented this whole scheme. You know, we started out in the 1600s with classical mechanics. Isaac Newton figured out the way the world worked according to a very simple set of rules. And this set of rules was so good, so compelling, that the idea that classical mechanics was not right just never even entered people's minds. It was a framework in which you could do physics and everything else from electromagnetism to Einstein's theory of general relativity fit into the framework of classical mechanics. Quantum mechanics is something entirely different. It's not an improvement on classical physics. It's a replacement, wholesale. Newton was wrong. Quantum mechanics is saying something very different. And there's no place more vivid than this picture that you've all seen, the cartoon of an atom, the Rutherford atom. I love giving these talks in England because all these things happened in England, right? And Newton, classical mechanics, Rutherford did his work here at Cambridge.
Time to go fishing!
And Rutherford says, we knew about atoms. We came up with atoms in the 19th century.
Well,
but
she's
then
got
there was
that
this
ace.
plum pudding model where the atom was a big fuzzy thing with charges distributed inside. It was Rutherford who showed that's not right. The atom has most of its mass concentrated in the center, in a nucleus, and then electrons are very light charged particles that orbit around the nucleus. And this is still the picture you are shown today, right? We've all seen this picture, and there's some usefulness to this picture. It gives some intuition about what's going on. It's really the electrons that are doing all the work in something like chemistry or electricity in a material or something like that. The heavy nucleus just sits there. The electrons can jump from atom to atom. But I'm here to tell you this picture is nonsense. It is not the real world. And I can tell you why it's not the real world, because as I alluded to, in the 1800s, people like Michael Faraday invented something called the theory of electromagnetism. James Clerk Maxwell especially put the finishing touches on it. And according to that theory, if I have a charged particle like an electron, there's an electric field coming out of it. So if I move the electron a little bit, the electric field shifts to point toward where the electron is. So if I take the electron and I shake it up and down, there's a wave that propagates out from the electron, and we call that light. We call that electromagnetic radiation. All of the light in this room comes from shaking electrons up and down and watching the vibrations distribute in all directions. Guess what? This picture has an electron zooming around in a circle. It should be emitting electromagnetic waves. It should be emitting light to beat the band. And that means the electron should be losing energy. It should not stay in a stable orbit. It should actually spiral toward the center of the nucleus. And that should happen very quickly. You can run the numbers. You can do the math and show that it takes about 100 billionth of a second for the electrons to go from their orbits down into the center of the nucleus. So here's an experiment with numbers. You can do the math and show that it takes about 100 billionth of a second for the electrons to go from their orbits down into the center of the nucleus. So here's an experiment we can all participate in right now. We can ask,
would explain
here's
why.
a table, there's atoms in it, here's you and me, there are atoms, and I predict that if classical mechanics is true,
old and
100 billionth of a second from now, it will all collapse into a point. Ready? There. It didn't happen. So there's something deeply wrong about classical mechanics, and it took a long time, it took a lot of smart people thinking in different ways to come up with an explanation of what might be going on. Here's the explanation they came up with, and it's really dramatic, and even though it took a while, to be honest, it's amazing that they came up with it as quickly as they did. The explanation is that electrons are not particles. It's a pretty dramatic explanation, so I want it to sink in, that electrons are deep down, they're really waves. Rather than thinking about the electron as a little point moving in an orbit like a planet in the solar system, you should think of the electron as a cloud, a wave-like cloud concentrated near the atomic nucleus. And for those of you who are tortured by chemistry classes as college students, you recognize these orbitals, which are the different shapes that electron wave can take. Just like if you have a string that is tied down at both ends and you pluck it, there's sort of a fundamental frequency, then there are higher harmonics. Likewise, the electron wave has its lowest energy state and then various higher energy states where it looks more complicated. So the reason why the electron does not spiral in and collapse to the center of the nucleus is because its lowest energy state is not sitting point-like at the center, but being spread out like a wave. Okay? Circa the mid-1920s, people came up with this idea. And you can actually explain data using this. You can explain why the light emitted by atoms has a certain form. Even better, there's an equation. It's important that I show you the equation because at the quiz that will be handed out at the end of the lecture, you will have to do some problems. Sorry. This is the Schrödinger equation invented by Erwin Schrödinger. And actually, we're not going to go through the details here. The point is that there is an equation. It's very pretty. It's like a little piece of concrete poetry, if you want to think about it that way. But the point is that not only do we have an idea, electrons are waves, not particles, we have a new equation to replace Isaac Newton's equation. Isaac Newton's equation is F equals ma, force is mass times acceleration. You tell me where a particle is, how fast it's moving. Newton's laws in classical mechanics will tell you what it's going to do next. In quantum mechanics, you tell me the wave function, very boring name, sorry about that, the wave function of an electron. Schrödinger's equation is going to tell you what it does next. On the right-hand side of the equation, it asks how much energy is there in the wave function. On the left, it says here's how fast it's going to evolve over time. So that makes physicists very happy. Equations are what make warm their heart a little bit because it's full employment, really, for physicists. And it's certainly full employment for physics students. Solving the Schrödinger equation keeps them up at night when you're second-year undergraduates doing your quantum mechanics. Here's the problem. Exactly because you have an equation and the equation is unambiguous in what it says happens, you can say, not just for electrons in orbits, but for any phenomenon, period, the Schrödinger equation should apply. If you're saying that quantum mechanics is a fundamental replacement for classical mechanics, you can use this equation to make all sorts of predictions. Here's a kind of quantum mechanical phenomenon. A nucleus of an atom might be unstable, right? It decays. And when it decays, it might emit an electron or another charged particle, and the Schrödinger equation will predict how that electron gets emitted. Remember, the electron is a wave. The way it gets emitted will look more or less like these. It'll be like some big spherical cloud that moves away from the radioactive particles. Here's what it actually looks like. This is a real picture of a little bit of uranium in a cloud chamber that is emitting radioactive particles, and when the charged particle moves through the chamber, it excites the atoms around it, and they leave a little track. Okay? So these little trajectories represent particles being emitted from the radioactive substance. What you immediately see is that they're all straight lines. They're trajectories. It's as if a particle has moved through once it was emitted from the radioactive substance. That is not what is predicted by the Schrödinger equation. The Schrödinger equation says there should be a wave, big puffy thing going out in all directions. What you see when you look at it is as if the electron looks like a particle. So it's almost as if the electron is kind of like a wave when you're not looking at it. But it's a particle when you look at it. Okay, so in the late 1920s, the greatest minds in physics thought about this. Einstein, Bohr, Schrödinger, Dirac, Pauli, Heisenberg, and they came together, they had meetings, and they fought and everything, and they came up with a theory of what was really going on. And their theory is the following. The electron is like a wave when you're not looking at it, and it's like a particle when you look at it. sadly, this is the state of the art, even today, and it's called the Copenhagen interpretation of quantum mechanics. So the way that we resolve this apparent paradox is to say that the electron over here on the left, it has a wave function, it's a spread out kind of thing, some kind of cloud, but then when you look at it, the wave function changes suddenly, dramatically, and unpredictably. You don't know exactly where it will change, but it will collapse onto a point, so it looks like a particle, and the best you can say is to predict the probability that the location of that new particle will be here or there. And the rule is, the bigger the wave function at any one point in space, the higher the probability that the particle will be found there. Okay? These are the rules of quantum mechanics as we currently teach them. Here they are in a little bit more formal form. This is what we teach our students. I'm not making this up. I will not at the end say, ha ha ha, those 1920s physicists just weren't that smart. This is still what we teach our students today. There are two sets of rules for quantum mechanics. The first set of rules apply to quantum systems when you're not looking at them. And they say there's something called the quantum state of the particle, which we call the wave function. And there's an equation that exactly governs what the wave function actually does in time. This is precisely parallel to classical mechanics. There's a state, and there's a set of equations that tell you how they evolve. But classical mechanics stops there. Quantum mechanics has a whole new set of rules for what happens when you look. When you look, the wave function changes. Suddenly, it collapses to a particular value, collapse of the wave function, and you don't know where it's going to collapse to. All you can do is say the probability. This is what we teach people in textbooks. So this should bother you a little bit. It's not your fault if it's bothering you a little bit. You should actually be bothered. Many people are bothered when they're students and they first hear this, and when they ask questions, they are told to shut up. And if they keep asking, they're told to leave the field of business. But just to explain this a little bit more, let's, my favorite thought experiment, of course, Schrodinger's cat, right? This is something you've heard of before. Schrodinger's cat is not meant, like a lot of people think the point of the Schrodinger's cat thought experiment is to impress you with how counterintuitive quantum mechanics is. Schrödinger and Einstein were two people who, when this formalism of quantum mechanics was invented, didn't buy into it. Schrödinger, despite having invented the Schrödinger equation, once the full formalism was put together and the interpretation of his equation was as a way to get probability of things, he literally said, I wish I'd never had anything to do with this. He did not return his Nobel Prize, but, he momentarily felt bad. The point of this thought experiment, which Schrödinger and Einstein invented over the course of letters sent across the Atlantic Ocean, was not to say, wow, quantum mechanics is impressive. It's to say, surely you don't believe this, okay? So the point is to take a quantum wave function that puts a certain system in a superposition of different possibilities and amplify it from a microscopic system to a macroscopic system. So he takes a radioactive decaying nucleus and puts a detector next to it, which will say, okay, it's decayed or it's not decayed. So according to the rules of quantum mechanics, the nucleus has a wave function that is a superposition of both I've decayed and I've not decayed. So the detector is in a superposition of I have detected you decaying and I have not. And according to this gizmo that Schrödinger imagines, if the detector clicks and sees a radioactive decay, it opens up a container that has gas in it. And the gas fills the wider box that's contained in it, which also contains a cat. Now, in Schrödinger's original formulation of the thought experiment, the gas was cyanide. His daughter later said, I think my father just didn't like cats. I love cats. So in my version of the thought experiment, it's my lecture, it's sleeping gas in the box, okay? So according to the rules of quantum mechanics, the cat evolves into a superposition of I'm asleep and I'm awake. So it's really important, all these words in that sentence. It's not that we don't know whether the cat is asleep or awake. It's that the state of the cat, according to the rules I just told you, before we observe it, literally is both. A little bit of both. A superposition of both awake and asleep. In other words, classically, we could describe the cat as maybe it's awake, maybe it's asleep, I just don't know. That's an epistemic question, not an ontological one. It's a question about what I know, not what really is. Okay? Quantum mechanics is saying something different. So the notation here is classical things are in square brackets, quantum things are in parentheses. Quantum mechanically, the cat can be in a superposition of both awake and asleep at the same time. And then Schrödinger says, if I believe the malarkey you were trying to sell me on the previous slide, only when I open the box and observe it does the cat become one or the other. So let's tell that story according to the textbook interpretation.
Time to go fishing!
Part of the ideology of textbook quantum mechanics is that the observer, the physicist, doing the measurement, is treated as if they follow the rules of classical mechanics. So even though you are made of atoms, and we all think the atoms obey the rules of quantum mechanics, according to the Copenhagen interpretation, you do not obey the rules of quantum mechanics, you obey the rules of classical mechanics. So the cat is treated quantum mechanically, parentheses. The observer, in this case played by Niels Bohr, is treated classically. Okay, so there's no wave function for the observer. What happens is the observer opens the box, the cat was in a superposition. Once that observation gets made, either the world is such that the cat was awake and the observer saw it awake, or the world is such that the cat was asleep and the observer saw it asleep. Two different distinct choices, and you can calculate the probability of either one. The problem is, this is clearly crazy pants. This is nutso. No one could possibly take this seriously as a fundamental theory of nature, right? I mean, there's many issues here, and people like Einstein and Schrödinger raised their hands in the back of the room and said, surely you can't believe this, and no one listened to them. So let me just mention two of the problems that are very, very clear here. One is very famous and has been mentioned many times, the measurement problem of quantum mechanics, right? In those rules I taught you, there's a role played by observation or measurement, by looking at things. So the measurement problem is just, what do you mean, look at something? Does it have to be a human being looking at it? Can the cat look at itself? Does that count? What if it were not a cat? What if there were just a video camera? What if we're an earthworm or an amoeba? What if I just glance at it? What do you mean a measurement? When does it happen? What qualifies as a measurement? How quickly does it happen? Is it instantaneous? Why is it probabilistic? And again, if you're in the back of the room in your quantum mechanics class and raise your hand and ask these questions, you're told not to ask these questions. You're not given sensible answers. But there's an equally bad problem that I call the reality problem. I said at the beginning, the electron is a wave called the wave function. But is it really? Because the whole point of those rules is that we never see the wave function. Whenever we look at the electron, it looks like a particle. Is the wave function really representing reality, or is it just a tool we use to predict the outcomes of potential measurements we could do? Or do we need more than the wave function? Is wave function part of reality, but not all of reality? What is reality? We don't know. And this is why, in many discussions of quantum mechanics that physicists try to give to wide audiences, they get confused themselves. You know, is the atom mostly empty space? No, if you think the atom is mostly electron wave function. But yes, if you think the electron is secretly a particle inside the wave function. So we don't know the answer to these very, very basic, easy to ask questions that should be embarrassing. There's a long history, of course, of young people entering the field and saying, I'm going to answer these questions, and then being kicked out of the field. One such person was Hugh Everett, who in the 1950s came up with what is called the Everett interpretation of quantum mechanics. He didn't call it that, but you know. And the wonderful thing is that Everett, in some sense, was being more of a therapist than a physicist. He was giving a way for physicists to accept reality in a way that they apparently were in denial about. To these questions, what is reality, what happens at a measurement, he offers very simple answers. He says the wave function represents reality. That's it. There's no extra stuff, and it's not just a tool to make predictions. It is isomorphic to reality.
Come on, you
That's
slut.
it. And what happens when you make a measurement? There's no collapse of the wave function. There's no sudden, unpredictable, probabilistic, stochastic thing. There's just the Schrödinger equation. The Schrödinger equation applies all the time to everything in the universe. Bold words indeed, but we already gave an argument that can't be right? Because the Schrödinger equation predicts the things coming out of the uranium should go in all directions, but we only see them go in trajectories. But still, before we resolve that, I do want to make it very clear how simple this theory is, right? Compared to the Copenhagen interpretation, the rules of Everettian quantum mechanics are beautifully simple. He just erases all of the rigmarole about observations and measurements and collapses. He says there are wave functions and they evolve according to the equation that you already know. He doesn't add anything at all to the formalism of quantum mechanics. He just takes things away. The problem is, how in the world can this map onto the reality that we see, map onto the reality that says when we look at electrons, they look like particles? So let's look at, there's two things that Everett made use of that are absolutely part of quantum mechanics. He's just saying you should accept them. One is the fact that you are made of atoms, and therefore you are part of the quantum world. You are not classical. That might be a nice approximation that works in certain circumstances, but honestly, the observer should be treated quantum mechanically just like the thing being observed. The other thing he makes use of is a phenomenon of quantum mechanics called entanglement. This was something that was really first emphasized by Einstein. Einstein, if anything, is underrated. He's rated pretty highly, I know. Man of the century, right? Person of the century. But there's this reputation that by the time quantum mechanics was put together in the late 1920s, there's literally a conference, the Solvay meeting in 1927, where Einstein and Bohr and the others hashed out the rules of quantum mechanics. And there's this speech we give ourselves about how by that time Einstein was a little bit old, he was slowing down, he was too conservative, he couldn't keep up with the new physics. He was 48.
I'm 48.
I do not want to admit that at that age one is too old to keep up with the latest advances. The truth is that Einstein understood quantum mechanics better than anyone. The problem was he didn't accept it. He didn't think it was done. He didn't think that the Copenhagen interpretation was good enough. And one of the things he invented by thinking hard about it is this phenomenon of quantum entanglement. So I will illustrate it by thinking about the Higgs boson, discovered just in 2012. They didn't know about it in Einstein's time, but it's a nice illustration because other than the Higgs boson, every particle, every fundamental particle that we know about in nature has what we call spin. It rotates. And because of the rules of quantum mechanics, just like when you look at the cat inside the box, you never see it in a combination of awake and asleep, an electron that is spinning, when you observe the spin, you always see it's either spinning clockwise, which we call spin up, or it's spinning counterclockwise, which we call spin down. It's never actually any superposition of those two possibilities. The rules of quantum mechanics say that when you're not looking at it,
I love challenges like this, where I come into the game and we're behind.
Does
if
not
I can
have
fuck
any spin,
holes,
but it
win.
can decay into two particles that are themselves spinning. And the nice thing about that is the total amount of spin in the universe stays the same when that happens. So if a non-spinning particle converts into two spinning particles, you know that the two spinning particles have to be spinning in opposite directions so that their spin cancels out. So here is the quantum mechanical prediction. The Higgs boson, with zero spin, decays into two particles, a particle and an antiparticle. We don't know, if we were to observe the spin of either particle, what answer we would get. But we do know, if we observe the spin of one of the particles, the other one is opposite. So the thing that the Higgs boson decays into by the rules of quantum mechanics is a combination, a superposition of particle 1 is spin up, particle 2 is spin down, plus particle 1 is spin down, particle 2 is spin up. There's no possibility if they're both spin up, that would violate the conservation of spin, the conservation of angular momentum.
Well, that's fine.
Okay? So this just comes out of the need to preserve conservation of angular momentum, but it's a very profound thing. This is saying the following very, very big difference between classical mechanics and quantum mechanics. In classical mechanics, you have a bunch of particles.
That whore.
One by one. This particle's doing that, this other particle's doing the other thing. For quantum particles, they each have a wave function. Particle 1 is some combination of spin up and spin down, so is particle 2. But no, that is not how it works. There are not separate wave functions for every bit of the universe. There is only one wave function, whatever it called the universal wave function, what Stephen Hawking calls the wave function of the universe. And according to the wave function of the universe, these two particles are related. They are entangled. We don't know what answer we will get if we measure the spin of particle 1, but we know that it will be the opposite of the spin of particle 2. This is something that they didn't really know about in the 1920s, but Einstein and his friends pointed out in the 1930s, and it wasn't until 20 years later that Hugh Everett put it to work to understand the measurement problem. So here is the Schrodinger's cat experiment according to Everett. There is only one wave function, the wave function of the universe, and you are part of it. So now the observer is in parentheses. The observer is a quantum system. The role of the observer is now being played by Hugh Everett. And we're not going to have any magical wave function collapses, etc. All we're going to do is run the equation, the Schrodinger equation. You and I obey the Schrodinger equation just like electrons and cats. So when you open the box, there's nothing mystical, nothing magical, nothing sudden. There is an interaction, a physical relationship that comes into being between the observer and the thing being observed, and that entangles those two things. So it is absolutely unambiguous that the Schrodinger equation says that what you get when you open the box is a superposition that is entangled such that the cat's awake and the observer saw it awake, or the cat's asleep and the observer saw it asleep. Everyone agrees. That's what the equation predicts. The problem is, no one has ever opened a box, looked inside, and felt like they're in a superposition of having seen the cat awake and having seen the cat asleep. No one has ever felt like they're in a superposition of having seen the electrons spin up and spin down. So it's not that this makes no sense mathematically. The claim is this is not the world. This is not the world that we experience, okay? How, Mr. Everett, are you going to map this very beautiful theory onto reality? The answer is I left something out. Maybe you were clever enough to catch that I cheated a little bit. I just told you there's not a separate wave function for every bit of the universe. There's only one wave function for everything at once. And yet, I wrote this wave function as if the only thing that exists is a cat and Hugh Everett. I really should technically include the entire rest of the universe in my wave function. Do not be alarmed. This is easy to do. We invent a word for the rest of the universe. We call the environment. Here's a picture of the environment, okay? It doesn't matter. So the environment with a specific state doesn't really matter. What matters is the environment is going to interact according to the Schrodinger equation with the cat and with the observer. So the environment, for example, in this room, it's everything I don't keep track of. It includes all the atoms in the air. It includes all the photons of light coming from the light. Oh, look, there's a whole balcony up there. Hi, everybody.
Well, we know how you got a king or a
You're not part of the environment. I do care about you. But in the box, there's the environment as well as outside the box. So what happens is, long before you open the box, the environment, the photons and the atoms inside the box interact with the cat. You know, you imagine if the cat is walking around and awake, a certain photon might be absorbed by the cat, whereas if the cat were lying down and asleep, the same photon might go right on by. So this is a phenomenon called decoherence. That cat does not maintain its separate identity just by being in two different places, depending on if it's awake or asleep. It instantly becomes entangled with the environment. So we have a situation where before I've opened the box, there's a cat that's awake and the environment has measured the cat to be awake, or the cat is asleep and the environment has measured the cat to be asleep. And then I open the box, and that's what I call measurement, but the action has really already happened. I then become
to the sun again.
That king. That fucking pisses me off. Infinity. No. Infinity. Infinity. No. Infinity. Infinity. No. Infinity. Please shit at me, please. That whore, that whore, that whore, that whore. Come on, slut. Oh, wait a minute. We're not playing chess. King shit on me, please. Son of a bitch. That piss ass score.
It started with a kiss. You pulled me close, held my gaze, whispered to me. You never felt like this. What was I to do? What was I to say? To say. All I wanted was to run. All I needed was to stay. To stay. When worlds collide and everything alive.
Yeah, look at this. Man, look at this hand job. Man, I got a hand job here. Look at this fucking shit. Man, look at this fucking shit. No! No need to give, no, time, not time to go fishing. Let's hope he doesn't have that damn king. Bitch, what a... Yeah. Night. That whore, that whore, that whore, that whore. Spirit. No. That looks so fucking ugly. Man, that looks so fucking ugly. I want to kill myself sometimes. We spit, spit, spit. I'm the Duke of. Cause I'm the Duke of. L. Damn. Damn, I forgot game tonight. That whore. That whore. Throw something beside the damn diamond, dumbass. No. Is that all that motherfucker to control the fucking diamonds? Come on, slut. Throw something out, slut. Whoo! Now I'm safe. Let's out of fucking spades. I fuck that. Oh! Hey, you're welcome. You know. I forgot it's game show night tonight. I'm so ashamed of myself. 1, 2. That whore. Man, I'm just fucking up totally. Why am I forgetting stuff? That fucking pisses me off. That whore. Man, this guy I'm playing with is a moron. Fucking moron. Hey, Courtney, I tried calling you at the Bible study, but when I got home, I realized I was calling the wrong number. But we figured that's best because my birthday. Did you get the message I left on your messages? Answering machine. We're gonna celebrate my birthday party next Monday, and we think it would be better if you called us then. Yep. I called the number. I thought it was 30. I called 308-235. Oh, I'm sorry. You get the picture. I called the wrong number. So I'm gonna program it. I'm gonna program your number in my cell phone. And then when I call you, I'm going to give you their number so you can call them and they can put you on speaker. Oh, Courtney, don't give me a number in the broadcast. You don't want everyone else to know. I just caught myself trying to almost doing that. Don't give me a number in the broadcast, Courtney. I know you can trust everybody here, but you don't want. I'll probably have to make this video private on my YouTube. Hon. Give me a second. Yep. And the day's supposed to be game show night. I feel really bad. Little Bill, let me go invite Caitlin. No, I can't because, I bet you've never seen me play this game before. Oh no, Courtney. Made in China. What a crock of shit. That was a good counterfeit. That rhymes, just like a smelly Shelly. Cause she rhymes. And nothing rhymes with her name. I've never seen Gucci, so I wouldn't know what it looks like. Well, I take that shit back and get a refund. Think about it, Courtney. Are you ever gonna find some Gucci at a Goodwill? No. And what about my Gucci bag? This is Spades. Man, look at this shit. I hate hands like this. Screw it, I'll just go nil. I'll probably get set, but I'll just go nil. Because I got that damn king of spades. Well, you gotta play fall suit, but if you're avoiding the suit, you can trumpet with a spade. The ace of spades is the highest card you can get. Let me. I told him, he said his hands were so terrible. I said, you got one of those hands, you got one of those toilet paper hands the dealer wiped his ass with. Yeah, I think I've gone to Goodwill before. You can get some good clothes there. Oh, I just messed up. There you go. Yeah. Well, let's change games. I messed up. They didn't wash nothing. They're too late. It's too expensive to have to wash them clothes. You think they're gonna wash the clothes? No. Oh yeah, let's play some damn chess.